In our previous videos, we talked about what makes bonds happen, right? Covalent bonds, ionic bonds, the energy of them, but how do bonds form? We haven't really talked about that. We talked about the fact that they're energetically favorable. We got these negative charges and these positive charges that want to be close to one another, but how do they do that? So to consider that, we need to talk about how bonds actually form. And the way that they're going to form involves overlap, and overlap is going to lead to bonding. Right. Now, the way that things bond is that they're going to share electron density. Right? The electrons around one atom, like we see perhaps down here in one hydrogen, wants to be shared with the nucleus of the other atom. To do that, we basically have to put the electrons from atom 1 into the electron zone, right, into the same area that the orbitals exist in atom 2. And what we see is this type of overlap right down here, where we've got this area where both of my orbitals overlap. Right? So we see that with two s orbitals. We can see a similar thing between an s orbital and a p orbital, or between two p orbitals, where we have these areas of overlap where each atom gets to have some electrons and share that electron density with the neighboring atom. So these bonds are only going to happen where we see overlap. Point number one. Right, now we saw this graph, or one very similar to it, previously. Right? To get to our equilibrium bond length, right, our stable bond length, we have to bring these atoms together initially so that there's any overlap. Then we get a very small amount of overlap, and then our equilibrium bond length, we have a fair amount of overlap where the electrons can be seen by each nucleus, but we're not so close as to where the nuclei would start to come closer and closer together. Let me draw that up here perhaps, where we had a lot of overlap and our nuclei would be very close and really repelling one another, right? So the energy goes way up. So we want to have good overlap. Electrons are shared nicely in these covalent bonds, but not so much overlap that the nuclei start to repel one another. For our hydrogen-hydrogen bond, our equilibrium bond length comes in at about 0.74 angstroms. Just FYI. As we start talking about this idea of overlap, however, we hit a disconnect. Because on one side, we have these covalent bonds where overlap is really important. And we talked about all these atomic orbitals. But on the other side, we have molecular geometry. And if you remember our molecular geometry, we had all these fun shapes that had a bunch of different bond angles, right? 180, 120, 109.5, right? All of these are based on those idealized bond angles, and we can make almost none of those from our atomic orbitals, right? These are all either spheres or things that really exist at right angles. So we have 90 degrees, and if we're super generous, we can say we have 180 degrees. Where do we get 120? Where do we get 109.5? How does that happen? In order to get to those, we have to do something called hybridizing the orbitals. So we're going to end up with hybrid orbitals. Remember we had the resonance hybrid when we combined things? This is going to be similar. Here's just a little bit of text information to help you sort of organize all the important terms. Right? So we've got orbitals, and when they bond, they're going to overlap. And these bonding orbitals are not the same thing as our atomic orbitals. Right? So how do we get from that nice starting place where we said we got s, p, d, and f orbitals to these atomic orbitals? We undergo a process of hybridization to make the hybrid orbitals. Right? Now these hybrid orbitals, when we add up everything, add up the atomic orbitals that we need, they're going to give us the bond angles that we want. Let's look at an example. We're going to make some bonds with beryllium. All right? Now beryllium, Be, if we drew a Lewis symbol for it, we know it would have 2 electrons in its valence shell. It's got 2 core electrons as well, so it's got 1 s2, 2 s2. All right. How do I make bonds out of this? Right? If we remember, when we want to form bonds, we want to pair up electrons. But here I have 2 electrons, and here I have 2 electrons. There's no unpaired electrons to form a bond with. So how do I get from this idea right here down to this Lewis symbol where I've drawn electrons on two different areas of the atom? What we're going to do is we're going to start mixing and matching. And kind of the first step of this is that we're going to take this paired electron, right, our downspin electron in the 2s orbital, and we're going to promote it up to the 2p orbital. So now I've got two unpaired electrons ready to bond with something. Now this doesn't look like it's a really good plan because our 2p orbital is, of course, higher in energy than the 2s electron that I started with. All right? So we don't really end up with a 2s and a 2p electron. We want these two to be equal. So we're actually going to take these two orbitals and combine them. Now what does that look like? So I've got this 1s orbital and I've got a p orbital. And we're going to mix and match them, which really what it means is we're going to take the mathematical function that represents an s orbital and the mathematical function that represents a p orbital. Right? Remember, orbitals describe where we're likely to find an electron. They're a probability function. All right? And we're going to take those two probability functions, add them together, and average them out. Now, since we start with two orbitals, in terms of our atomic orbitals, we're going to end with two orbitals. Right? Our number of orbitals needs to be conserved. Right? So we start with an s orbital and a p orbital, and we end up with two sp orbitals. Right? So these are sp orbitals, right? Because they're made of one s orbital and one p orbital. If we put them on top of one another, we get a shape that looks like this, which is notable because right away we see, oh, the angle between this left-hand one and this right-hand one is 180 degrees. Two bonding groups, two bonds, 180 degrees apart. That's pretty good. All right, so once I have generated these two sp orbitals, right? So we have sp orbital number 1, sp orbital number 2. They can then overlap with whatever we're trying to attach to the beryllium. So here I've got two different fluorine atoms. My fluorine atoms are going to start with one unpaired electron in a p orbital. All right, that's going to come and overlap with that sp orbital right here, giving us a pair of electrons, and on this side, giving us a different pair of electrons. And again, I've got that 180 degree bond angle from beryllium fluoride, or beryllium difluoride. So our hybrid orbitals help explain the molecular geometries that we see. All right? Now, notably at this point, I want to point out we can't directly observe hybrid orbitals. Right? We can do a bunch of math and say, hey, this is what the shape looks like it's going to be. But we use orbitals to explain geometry, right? Not the other way around, right? We can directly observe the geometry. We know we're certain about this. Hybrid orbitals are our best explanation for how we managed to get those shapes out of atoms in the first place. Energetically, what's going on, all right? Because where does the sp orbital fit in terms of either the 1s or the 2p orbital, the 1s orbital that's lower, or the 2s and 2p orbital that we started with? Right? Because missing here is, where'd my 2s go? Well, when we promoted that electron, we really did move it around. Let's shift this down a little bit. Whoop. There we go. Here's my one beryllium atom, and I started with those two electrons in the s shell. And then I promoted one up to the p shell. I'm going to mix those two together. So I've got two p orbitals that I didn't do anything to. And now instead of a 2p orbital and a 2s orbital, I've combined those to make an sp orbital. Now, since I had one of each, energetically, it falls pretty much directly between where the s orbital was and where the p orbital is. All right, so now I've got two p orbitals and two sp orbitals, and I can make two bonds, right? Or at least two single bonds. I'll come back to the rest of that later. Speaking of later, that brings us to the end of what we're going to talk about in this particular video. Come back to the next one, and we will look at our other hybrid orbitals, starting again with an sp orbital, talking about sp2 and sp3. See you then.